This is the key to your Unit 4 study guide, Structure of the Atom. I've already gone through and done most of these, so I'm just going to give a few explanations here and there so that you kind of know what I was thinking. I filled this out as I would have as a student to try to help me study, so hopefully it helps you as well. So you're contrasting beta, gamma, and alpha radiation. So to make my chart, I listed the three. Here I have the symbols that we use for each type, and then each type of particle that is given off for each type of radiation. For alpha, it's 2 protons and 2 neutrons. For beta, it's an electron, and gamma, it does not give off a particle, it just gives off energy, so I made a note of that. The mass that is going to be, that's going to go along with each particle, I wrote over here as well. 2 protons and 2 neutrons equal up to a mass of 4. An electron doesn't weigh anything, and energy definitely doesn't weigh anything. And then over here, I went ahead and put what would happen to the atomic number if something were to undergo each type. If something undergoes alpha radiation, the atomic number is going to go up, going to go down by 2 because you're losing 2 protons. If it undergoes beta radiation, the atomic number is going to go up by 1 because your neutron is splitting to an additional proton, making your atomic number go up, and then that electron is ejected as your particle. Gamma is just energy, so your atomic number doesn't change with that one. For number 2, we've made this chart a few times, so I figured you guys could handle it, but here's the key just in case. For number 3, drawing the 2 regions of an atom, your 2 regions are going to be your electron cloud and your nucleus. I tried to represent the relative size of them with my drawing. You didn't have to, just as long as you know the 2 regions and that overall this entire thing is in fact an atom. Nucleus is the center of an atom and the electron cloud is around the outside. For number 4, it asks you to kind of talk about the size of each region that you drew your picture about up there. So in my answer, I just wrote that the electron cloud takes up most of the space, nucleus takes up very little. I talked about this in class, how the electron cloud takes up most of the real estate, and we had the comparison of if your atom were the size of a football field, then the nucleus would be a dime in the center. So a little bit of a size comparison you could also use. For number 5, remember that electrons are the same as protons in a neutral atom, but in an ion, they are not the same. The electrons are going to have been lost or gained, and that causes your atom to be charged, meaning that it's an ion. And then atomic number is equal to the number of protons. That's something you should know by now. And calculating number of neutrons, all you have to do is take your mass number and subtract your atomic number. Number 8, differentiating between mass number and atomic mass. I think this is really important and it's something some of you are having a hard time grasping. So I tried to write some really good definitions here. Your mass number pertains to an actual physical atom, one that is right in front of you. You can count them if you could count them. So the actual number of protons and neutrons in a specific atom. So you're looking at just one. That's the actual number that's in there. Atomic mass, though, takes into account all of the known isotopes of an element. So you're talking about multiple atoms, all of them of that particular element, actually. And it is an average of the mass of those known isotopes, and it's weighted according to their abundance, meaning how common they are. So the atomic mass on the periodic table is going to be closest to the mass of the isotope that occurs most often in nature. What happens to an element that undergoes alpha or beta decay? We talked about it on the previous page. The atomic number is going to go either up or down, meaning that they change into new elements. Number 10, definition of an isotope. They are atoms with the same number of protons but different numbers of neutrons, which means that they're going to have different masses. If I have one atom of potassium that has 41 neutrons here, and another atom of potassium that has 40 neutrons over here, this one is going to weigh more because of that additional neutrons. Neutrons have mass, so that means that the mass number is going to be different, even though the protons are the same. I think this question was pretty straightforward. I've labeled everything on the periodic table square. Just be aware that this is the atomic mass, not a mass number, which means I've drawn my arrow clear back up to here. The atomic mass is this right here that I drew my little definition of earlier. This is the one that's weighted according to the abundance. How mass number changes with each type of radiation, talked about in my chart, but just to sum up, for alpha the mass number is going to go down by 4. For beta the mass number stays the same because essentially you're exchanging a neutron for a proton, so a 1-for-1 mass exchange, and gamma is just energy, so it stays the same as well. So I just drew a little arrow. Number 14, definition of an atom: smallest unit of an element that retains its properties. That's important. Retaining the properties of an element. So I'm going to talk through one row on this chart, and then I'm just going to fill in the rest. But I'm going to talk through one just to let you know kind of how I go about doing this, and maybe it'll make it easier for you. So I have my atomic symbol, which means I can look at the periodic table and find my atomic number. So if I look at boron on the periodic table, its atomic number is 5. I automatically know that atomic number is number of protons, so I fill that one in automatically. It doesn't have a charge next to it, so I'm going to assume that this is a neutral atom. So if it's a neutral atom, protons and electrons are the same. So I can go ahead and fill that in as well. If I know that my mass number is protons plus neutrons, then all I had to do was add those two together. And then for atomic mass, that's not something that I calculate, that's something that has to come off of the periodic table. And so I look at the periodic table, and the atomic mass of boron, which takes into account all of its isotopes, is 10.811. So that means that this isotope, boron 11, is the most common because the atomic mass is closest to it. So I've completed the chart right here. Remember that not just atomic number can help you identify them. If only atomic mass is given, that can help you to identify an element in particular. Even if you're only given the symbol, that still gives you a lot of information. So if all else fails, look at the periodic table and it will give you a lead. So number 16, what is an ion? We're moving into ions now, so you need to remember that they are charged atoms. Rather than neutral, these are the ones that have a charge. So I'm going to go ahead and do 1 or 2 columns of this with you guys so you can kind of see how it's done here. So this I automatically know is an ion because it has the actual charge here beside it. That's how you know an ion when you see it. It has that actual symbol. So this is sulfur with a 2- charge. So I can go ahead and write that in there. And since I know it's sulfur, I know how many protons it has just by looking at the periodic table. Sulfur is number 16, so that's automatic. So all I have to do is decide whether this ion has gained electrons or lost them. So a neutral atom of sulfur is going to have 16 electrons, but this one is not neutral. It's a 2- charge. And since electrons are negative, we know that it has more electrons than protons. And since it has a 2- charge, that means it would have 2 more electrons. So you can look at it as a sort of math problem. Prior to this, you had 16 positive charges. And in order to get to a final answer of -2, you're going to have 18 negative ones. So 16 minus 18 will give you the -2. So you could look at it either way. So doing the same thing on this one, potassium as a 1+ charge. Looking at potassium on the periodic table, it is number 19. So that goes in there automatically. We know the charge is 1 positive. So that means that this one has more positive charges, or protons, than it does electrons, which are your negative charges. So if it has 1 more positive charge than it does negative, then that would mean that this number would have to be 18 as well. 19 positives, 18 negatives to give me a final charge of positive 1. So this is the entire chart filled out, taking into account the charges that are just right here by the symbols. And so I've decided how many electrons I would have lost or gained, and then I wrote off to the side whether they were gained or lost. And so in this one we had 2 additional electrons rather than our normal 16. We had gained 2 more, so I wrote gain off to the side. And so you might notice here, every time it says gain, we have negative ions, and every time we see loss, they are positive ions. That's something to take note of, something we'll be talking about extensively in the future, so be thinking about that. So now we're moving right on to number 18. You just try to decide which type of radiation each one is describing. Decay with no mass and no charge. The no charge tells you the difference between beta and gamma, tells you that it should be gamma. An electron is a particle ejected by beta decay. The least penetrating is alpha, can be stopped with a piece of paper. Most damaging is the one with the least mass, it's going to be gamma. I just said something that can be stopped by paper would be alpha. And then something that can be stopped by aluminum, it's a solid object, so beta would be stopped by aluminum. Moving down to this section, it's just finishing out some nuclear equations. And so for beta, we talked about in our chart how your atomic number is going to go up by 1, but your mass is going to stay the same. So, I just miswrote that. So, my mass is going to stay the same for beta. That tells me it's beta right there. But my atomic number is going to go up by 1. So then I look at my periodic table and find out what's the atomic number, what has the atomic number 20. So this is going to be calcium. And that's all you have to do across the board. For alpha over here, we talked about how your atomic number is going to go down by 2 because you're losing those 2 protons. At the same time, you're losing 2 neutrons as well, which means you're losing 4 mass units. So mass is going to go down by 4, so we're going to be at 235 here. And the infamous number 92 on the table is uranium. So you keep looking at it kind of with this idea in mind. No mass change, no atomic number change, so it has to be gamma. Mass went down by 4, so without even looking at anything else, that automatically told me that it's alpha. Here I'm going an alpha decay, so I've got to take my mass down by 4 and my atomic number down by 2. Atomic number of 1 is hydrogen. When asked to draw an atom at this point, you can do something as simple as this. Nitrogen 15. Nitrogen is number 7 on the periodic table, so you should have 7 protons in the nucleus and then 8 neutrons to get your 15. And it's a neutral atom, so 7 electrons as well. So you can draw something as simple as that. On this, everybody was kind of freaked out because they were having a hard time seeing the numbers, but not once does it ask you to look at the numbers on here. It says how many alpha particles are produced when uranium-238 decays to lead-206. So all the way to here. So how many alpha particles are produced? And you can see those. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 of them. All you have to do is read the chart. And then the second question says how many beta particles, so you just count those as well. So counting the beta particles, I come up with 6. So read the question before you freak out. That's the moral of that story. And then on down, writing an equation showing protactinium-229 going through 2 alpha decays to form francium-221. Kind of got it started already. I wrote down my atomic number, mass number for protactinium, going through an alpha decay. So my atomic number is going to go down by 2. So I'm going to go to an 89, mass number goes down by 4, so 225, which means I have actinium here. And then it says it goes through 2 alpha decays, so I've got to go through another one, just like this. And so that means atomic number goes down by 2 again. Mass number goes down by 4 to give me that 221 it's looking for, which means this has to be francium. So number 23 asks you to write a similar nuclear equation, but instead you're going to go 2 alpha decays. So I showed that here. There's 1, 2, followed by a beta decay there, followed by another alpha decay there. And this is the end result. So for our last little question here, we have our first decay series or decay chain, and it's showing the decay of uranium-238. So uranium-238 is the starting point, and then the arrows show you where you're ending up. So you're ending up down here at lead. So for question A, it says what is the final product in the decay series? Well, if you follow the arrows, what you end up at is lead. Simple as that. Then letter B says, using the figure, you're supposed to list in order each type of decay that uranium-238 goes through to become lead. So you have to know what type of radiation is happening between here, and then here and here. And the figure itself kind of gives it away. It says atomic number is along the bottom and mass number is along the side. So here, with the arrow going down, that means that your mass number is going down. There's only one type of radiation where your mass number goes down, and that's alpha. So every time you have one of these arrows, it's alpha decay. And anytime you have a little dash to the right, that means your atomic number is going up, as you can see on the bottom. So that means only one type that could be as well, beta. So it looks to me like your order should go as follows: alpha, beta, beta, alpha, 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 beta, beta, alpha, beta, beta, alpha. Sometimes it's just a matter of taking your time and examining what's in front of you. Just don't panic. If you have any questions, let me know, and I hope it was helpful.